Students, welcome to the next lecture on crystal structure. The first week we saw different types of material, ferrous, non-ferrous. We also saw alloys, composites, polymer material. Now, where is this difference coming? The big difference comes from crystal structure. So, now in the first lecture of this week, we will try to understand crystal structure. We will divide the lecture into two parts. We will have theory covered by me and the problem solving will be done by Dr. Amandeep. So, each lecture theory will be backed by problem solving, so that you understand and appreciate the course. In the content wise, we will first start with crystal structure, then crystalline solids, single crystal solid, polycrystal solid. Majority of the material which is available will be polycrystal solid. Then we have non-crystalline solids also. So, where is this crystal coming a big way is space lattice. We will understand what is a unit cell, which is nothing but a building block for a complete material. Then, how are these building blocks packed? So, we will try to see atomic packing factor, then coordination number. We will try to cover simple three cubic structures, simple cubic, face centered and body centered. However, there are 7 basic. So, we will try to cover 3 and maybe 1 or 2 more additional when the problem solving class is going on. And finally, we will try to have a recap. Crystal structure. Crystallography is an experimental science of determining the arrangement of atoms in crystalline solids. People talk about crystallography in a big way. The big difference between artificial diamond and original diamond is understanding the crystallography. Groups of atoms or molecule specifically arranged called as crystal. So, a study on it is crystallography. So, crystallographists study about crystal structure. This is an area which is coming up in a big way, because we are trying to look at exotic materials which has combinational properties, or we have hit the limits of various material. So, now we are trying to dope with some atoms so that the crystal structure can be modified little bit. So, when we take any solid material, it is classified as crystalline, polycrystalline and amorphous. Crystalline means it's single crystal. Today, we talk about single crystal titanium material for turbine blade applications because of their excellent mechanical properties. Polycrystalline are various crystals put together to form a single object. Amorphous are non-crystalline materials. Many of the polymers are amorphous in nature. Many of the glass material are amorphous in nature. All solid materials are made of atoms or molecules arranged in a specific order in some material called as crystalline solids. If the arrangement is not there, it is otherwise called as non-crystalline or amorphous material. So, basically the building block is our atoms, atoms to unit cell. Atoms are the smallest known material for us, right. So, again you can see electrons and protons and neutrons are there, but to a large extent from the metallurgy point of view, we always try to talk about only atoms. So, these are atoms. These atoms are arranged in some fashion. So, if they are arranged in an orderly fashion, it is called as crystalline solids. The principal form of solid structures is crystalline. You see, these are all the atoms. These atoms are bonded together and these atoms can be arranged in a unit cell. So, this is called a unit cell. So, this is a crystalline solid and here you see non-crystalline or amorphous material how does it look like? The crystal structure, how does it look like? So, crystalline solids are characterized by the ordered arrangement of their ions, atoms and molecules. This you see green one is orderly arranged, and you can see this violet atoms. These are nothing but diffused atoms between the basic atoms. Like this can be iron, all greens can be iron, all violet can be carbon. So, if it forms Fe3C or FeC. So, it is a substance in which the atoms or molecules are arranged in a definite repeating pattern in 3-dimensional. Metals normally form crystalline solids, but some ceramics are also crystalline. So, you should also understand this. Crystalline materials also, ceramic materials also can be crystalline. The spatial arrangement of their ions, atoms or molecule and on the composition, size and shape of the crystal, you can try to form. So, these are 2D forms, these are 3D forms, and this is the total solid which you see in reality. This two are seen in the microscopical views. Right? So, the spatial arrangement of their ions, atoms, these are all atoms or molecules and on the composition. So, this is the composition, red one and blue one composition, size, the shape and size of this. So, if the atom has to be joined here, it has to be equi-sized or a difference of maybe 10% variation. It generally what happens is it always sits in between. So, composition, size and shape of the crystal is very important. So, this is a single crystal, this is a polycrystal. Single crystal are periodic arrangement across the whole volume. Polycrystalline are periodic across a grain. So, this is a grain. So, if you see here, this is a grain. So, inside a grain, they have a crystal structure or they have a uniform arrangement. But between grains, there can be different arrangement. When you talk about single crystal, it is uniformly arranged across the whole volume. So, what is the advantage? When I try to pull or push, tensile, compression, shear, I get wonderful mechanical performance. I can dictate now the material such that it meets to the application. And how do you get this? You play with heat treatment, which we will discuss it in the upcoming lectures. Right? So, now I am sure you should be able to clearly understand crystalline and non-crystalline. In non-crystalline, polycrystalline and amorphous. So, these are polycrystal materials. So, when we talk about single crystal is a silicon. We talk about single crystal. Even at infinite length scale, each atom is related to every other equivalent atom in the crystal by translational symmetry. So, this is seen in single crystal. Silicon, you can have single crystal. When we talk about polycrystalline, it is a material made up of an aggregate of many small size crystals. Right? So, you can see here, this is a grain, and around the grain it is covered by a boundary, which is called as grain boundary. So, the grain boundary has lot of energy. So, when you try to etch it, it forms a depth. So, that is why when you see in microscopic image, you see a black color at the grain boundary. So, each of these grains will have different arrangements. All these things put together will be there in one material. So, the grains are usually 100 nanometer to 100 micron. So, again, how do you play with the grain size? When you do heat treatment, we play with the grain size. The polycrystalline with grain size that are less than 10 nanometer in diameter are called as nanocrystalline. So, you can, the size, we are talking about 100 nanometer to 100 micron. This is normal. When we go towards 10 nanometer, then it is called as nanocrystalline material. Nanocrystalline material has different properties. For example, gold, what it behaves at 100 nanometers, when you go to 10 nanometer grain size, it completely performs differently in terms of optical properties. It's different. Mechanical properties different. Thermal properties different. So that's why we say nanocrystalline. So polycrystalline is further divided into nanocrystalline. Nanocrystalline materials are talk of the town now. Now they are trying to make inserts, cutting tool inserts of nano grains. They are trying to make nanocrystal materials on top of alloys such that it has good heat extraction properties. Nanocrystalline is gaining momentum today. Non-crystalline solids. Non-crystalline solids are also called as amorphous solids. In an amorphous solid, atoms do not possess well-defined arrangement. If you look at it, it does not possess a regular arrangement. So what is the difficulty? If it does not possess a regular arrangement, then if you want to tweak the material to meet the engineering requirements, it is difficult. But in reality, these are the things which can easily get formed. So amorphous solid has its own advantage. Amorphous structures forms in a complex structure, polymer, and a rapidly cooled material. So it is used in glass. So amorphous structures forms in complex structures in polymers, like polymers are thermoplast, thermoset, elastomers. You also have glass in this property, and they are rapidly cooled. In non-crystal solids, the particles have little freedom to move since they are not arranged rigidly as in the other solids. So amorphous solids, polymers also come. So thermoset polymers also are there. So there is not much of freedom for the movement. So if you look at the volume to unit weight with respect to time, you can see how is the response. So volume per unit weight with respect to time. Why is this important? Because later in your manufacturing process, we will see casting, injection molding, where the starting material will be a liquid. So if it is a liquid, and how does it respond for a crystalline structure and for a non-crystalline or an amorphous structure? So if you see that for a crystalline structure, it has a sharp melting point. So as the temperature increases, at one particular point, there is a melting point. And then you can see that there is a heat of fusion, and then it becomes a liquid. So this is solid, there is a transition, and then it forms a liquid. Whereas when you try to take an amorphous material or a non-crystalline material, it has an amorphous structure. So there is not much of change in the temperature profile. So that means to say there is no sharp transition. So you see here amorphous structure, then it, as and when you keep increasing the temperature, it takes you to a super cooled liquid, and then it becomes a liquid. So here where exactly the change in slope happens, this point is called as glass transition temperature. So generally for a polymer material, we always call it as a glass transition temperature point, wherein which there is a change in weight to unit volume as compared to that of a crystalline material. Keep this in mind, because this information will be very useful when we see casting process or when we see injection molding process during the course. An amorphous material exhibits quite different behavior than the pure metal when it changes from solid to liquid. So there is also an expansion, please understand. So why is this expansion very important? Later, when you try to convert this liquid into solid, there will be a contraction of material. That concept we will see in casting. The characteristics change in the volume of a pure metal compared to the same volumetric change of the glass, you can see a difference. So now friends, you will try to understand why is melting point important, why is glass transition temperature point is important, and why are we so much worried about crystalline and non-crystalline material. So now let us understand space lattice, because till now what we were trying to discuss, we were trying to see atoms. These atoms are getting arranged. This is what we saw. But now let us understand in the three-dimensional space, what is it? So we are now getting into space lattice. A three-dimensional translational periodic arrangement of points in space is called lattice. An infinite array of points in three-dimensional in which every point has an identical environment to all others is called as spatial lattice. So now we are trying to look into how is the atoms arranged in the given space. So periodic arrangement of points, then you can see every point has an identical environment to all others is called as spatial type. There are two types of spatial lattice. One is called as square spatial lattice. The other one is called as cube spatial lattice. A equal to B, we will see that, and then A equal to B equal to C. So what are we trying to say? This is A and B. When we try to talk about a cube, A, B and C. Okay, spatial lattice can also be classified on the basis of dimensions. This is 1D, this is what we were discussing 2D, and this is 3D. You can, when we define a point I comma j, so this is 1D only I, this is I comma j, and this is I comma j comma k. So you have x, y and z. Right? The spatial lattice can also be classified on the basis of dimensions. So what we saw here, there are two types of spatial lattice, square and cube. So here you can see one-dimensional space lattice, two-dimensional space lattice and three-dimensional space lattices. Metallic crystal structure, there are 7 different types of Bravais lattice. There are many, but these are the fundamental 7. Every material is a building material block of some units called as Bravais lattice. So there are 7 different types of Bravais lattice. So this 7 is important. It's good that you understand and you can also memorize. Cubic, where A equal to B equal to C, A equal to B equal to C, where in which the angles are alpha, beta, gamma is all at 90 degrees. When we try to draw a tetrahedron, right? Tetrahedron, you are compressing and then you are trying to move it. So where A and B will be equal, which is not equal to C, where in which the angles can be alpha, beta, gamma all at 90 degrees. Orthorhombic system, where A not equal to B not equal to C, where alpha, beta, gamma, they are all 90 degrees. If you see here, they all have an angle of 90 degrees. And if you see here, interestingly, we are trying to say length A equal to B equal to C, AB which is not equal to C, A not equal to B not equal to C. And now what are the other variations? I will try to now change this angle. When we go into rhombohedral, you will see that alpha equal to beta equal to gamma, which is not equal to 90. That's rhombo. Hexagon, where in which you will see alpha, beta will be 90, gamma will be 120. So, now what are we trying to do? We are only trying to say the change in the angle. So, it should be 90 or 120, right. So, then when we try to see monoclinic, you see alpha equal to gamma 90, which is the same as the previous, whereas the beta is not equal to 90. So, the change is this one is not equal to 90, but these two fellows are 90. And the last one you see tericlinic, where alpha, beta, gamma, none of them are 90. Right. Let us go to here. A equal to B equal to C, it is a repeat. A equal to B not equal to C. A not equal to B not equal to C. This is just a repeat. This one and this one are repeats. Right. And then finally, it will be A not equal to B not equal to C. Right. And here the important points are the angles which are getting changed. So, axial length and axial angle plays an important role to decide the different types of Bravais lattice. Now, why are these things important? Cubic, tetrahedral, orthorhombic, rhombohedral, all these things has a direct influence on the physical property, mechanical property and their service condition exposure. It is very important. That is why we are trying to understand this more in detail. Unit cell. Unit cell is the basic crystal unit or building block of a crystal structure and defines the crystal structure by virtue of its geometry and the atoms position within. So, these are all the atoms positioned within, right. So, when we try to define this point, we try to say it is 1, 0, 0 or 0, 0, 0. These are all planes. Okay. The distance from one atom to another atom measured along one of the axis is called a space constant. So, this is how a unit cell is there and these are the planes. The unit cell is formed by primitives or intercepts A, B, C along x, y and z axis respectively. The unit cell can be completely described by the three vectors A, B and C when the length of the vectors and the angle between them are alpha, beta, gamma are specified. The three angles are alpha, beta and gamma are called as interfacial angles. So, where are they? Alpha, beta and gamma, they are called as the interfacial angles, and A, this is A, B and C, these are the distance A in the x plane, y plane and z plane respectively. At the point what they meet is P, Q, R on the xyz coordinates. So, the primitive unit cell, the unit cell that contains one lattice point only at the corner is called as the primitive unit cell. In some cases, the unit cell may coincide with the primitive cell, but in general, the former differs from the later in that it is not restricted to being the equivalent of one lattice point. So, these two definitions or clarity is important. So, you can see here and see this diagram, right. The unit cell which contains more than one lattice point is called as non-primitive cell. So, primitive cell and non-primitive cells. Now comes the question of how are these atoms getting packed inside a unit cell. What is a unit cell? It is a building block. So, now let us try to understand atomic packing factor, number of atoms which are packed inside a unit cell. So, that is called as atomic packing factor APF is defined as the percentage volume of units covered by the atoms, because there is also a free space. This is defined as the ratio of the total volume of the atom in a unit cell to the total volume of the unit cell. So, we are trying to find out the volume fraction of the atoms present. You have to now clearly map your understanding with primitive unit cell and non-primitive unit cell such that you can try to understand. This is defined as a ratio. What is defined? APF is defined as a ratio of total volume of atoms in a unit cell to the total volume of unit cell. So, this is called as relative density of packing. So, there are number of atoms into volume of one atom divided by the unit volume cell. So, what is the volume of an atom? So, this is a volume, right, the atom. So, you have to try to calculate the volume of a sphere. Now, the question comes is whether this atom sitting in the corner, is it sharing with 4 other atoms or is it sharing with another unit cell only, or how is it? The face where the atom is sitting, is it sharing another face atom, so another face plane, so that the atom can become half. Here it can become quarter, here it is half, and suppose if something is sitting inside, it is a full atom. So, number of atoms, these are number of atoms, and then volume of one atom, we know the volume of one atom, that divided by the unit cell gives you this APF. There can be problems in the examination to calculate the APF of a unit cell which is given. Coordinate numbers, this is the next important concept. The number of equidistant nearest neighboring atoms that an atom has in the given structure is known as coordination number. So, the coordinate numbers for a simple cubic BCC, we will see that FCC is 6, 8 and 12. The coordinate numbers cannot be more than 12. So, I would request you to think, why is this restriction coming? So, you can draw a cube. Right? And please go by the definition, the number of equidistant nearest neighboring atoms that an atom has in the given structure is called as the coordinate numbers. Right? So, now you will try to figure out how is this limitation coming. This can be an exercise for you. Now, let us first start looking into simple cubic. Simple cubic, there is one atom at each corner. 1, 2, 3, 4, 5, 6, 7, 8. There is one atom at each corner and this atom is shared by 8 unit cells. So, the N number, coordination number will be 1 by 8 into 8, it is 1. The coordination number for simple cubic is 6. The size of a unit cell atom is always constant as A. So, the atomic packing factor is volume of the atoms in the unit cell divided by volume of the unit cell. So, here it is going to be number of effective atoms into the volume of a sphere divided by unit volume is A cube. So, what you finally get derived is this. So, 1 by 4 pi r cube into A cube. So, 1 by 4 pi r cube divided by this I am representing as r cube. So, this will go pi by 6. So, the volume fraction is 52%. Now, let us take BCC. So, if you see simple cubic, the atoms are located at the corners. When we try to do BCC, you will see the atoms are located at the corners and in the body center you will have one more atom. So, now it will be along with one atom at each corner, there is one atom at the center. So, those cells are called as BCC, body centered cubic cell or body centered cubic. So, here apart from this simple 1 by 8 into 8, we have one more additional component. So, the coordination number of body centered cube is 8. So, now when we try to calculate the atomic packing factor, which is nothing but volume of the atom in unit cell divided by the unit cell, it is number of effective atoms into 4 by 3 pi r cube divided by a cube. You get the answer root 3 by 8 pi. So, which is 68% filled volume. So, in simple cubic it was 52, here it is 68. Now, you see, depending upon the atom's location and you define the body centered or whether it is simple cubic, you see the atomic packing factor changes. Now, when we do for face centered, what is face centered? In face centered, you will have the basic cubic, and at every face you will have one atom. So, 1, 2, 3, 4, you will have 5 and 6. So, when you try to draw a cube, so there are 6 faces, 1, 2, 3, 4, 5 and 6. So, in face centered you will have, at every face you will have an atom, okay. Along with one atom at each corner, there is an atom at each face. So, it is 1 by 8 into 8 plus 1/2 into 6. So, which is 4. So, the coordinate number of simple cubic is 12. So, the constant is A. You can see there what is the atomic packing factor. So, the atomic packing factor is pi by 3 root 2. So, pi 3 root 2. So, now the filling factor is 74%. So, when we look into it, cubic center is 52, BCC is 68 and then here it is 74. So, with this you can try to give some assessment about the material. So, now let us see what are all the metals which fall under various cubic cells. 1, BCC, you will have chromium, iron, molybdenum, tantalum and tungsten. So, 68% filling factor. You look at it, FCC, you will have 72%. Aluminium, copper, gold, lead, silver, nickel. So, all these people are ductile materials, and these ductile materials, when you have atoms, right, in each of these faces, so then what happens? There is a easy sliding possibility. So, because of this, you will have more amount of ductility in FCC materials. And in the tutorial, we will try to see HCP material. HCPs, you will have hexagon on the top and then hexagon in the bottom. You will have a hexagon in the top and then you will have a hexagon at the bottom. Now, you will try to see each of this. Here you will have atoms and we will try to see how is it getting packed. So, titanium, zinc and magnesium falls under the category of HCP. If you look more in details, you will understand there is something called as slip plane. Then what are the different possible slip planes? All these details are there, but that will take us beyond the course objective. So, we will stop here. All I have to tell you is there is atom. These atoms are arranged, and when they are arranged, it is crystalline. If they are not arranged, it is polycrystalline. So, polycrystalline means within a crystal there is several grains. Each of the grains, the arrangement can be different. Now, let us try to take an atom. Now, how are these atoms placed inside? So, you will try to understand a unit cell. From the unit cell, we studied about the atomic packing factor. From there, we try to look into also the coordinate numbers. So, with this understanding, because we are more focused towards manufacturing, with this understanding, we will try to move further down. In this lecture, what did we recap? We recapped what are the atomic structures, crystalline, non-crystalline, atomic packing factor, coordinate numbers, different types of structures, simple cubic, FCC, BCC, body centered. So, it is FCC and BCC, etc. we solve. I have given you one assignment. I have asked you, why can't the coordination number be more than 12? That's the assignment I have given. Please check and get back with the results. These are the references which we have used for preparing this slide. Thank you very much.